Today we're going to take a look at lesson 110. So 110, if you look up at the top of your title here, we're looking at equivalent representations of polynomial and rational functions. That's a very, very complex way of saying this. We're going to rewrite polynomial and rational expressions in equivalent forms. So if you go over the next slide, this is going to walk you through that sometimes in math, we can reuse the same equation, but written in different forms for different purposes. Okay, that's what this is saying right here. Because it's all words, I'll let you read that on your own later. But what you do need to know is we have different forms for different purposes. You have different mathematical forms for different purposes. This uses an Algebra 1 example. This form and this form, both are the same exact equation. If you graph this, it's the same graph because it's the same equation. They both have their purpose. All right. On this slide, we walk through what are the two forms that you could see for polynomial. There are two separate forms. There is a standard form and there is a factored form. Here's what you need to know. These equations are equal to one another. These are equal to one another. So if you want to put that in there, these are equal to one another. So again, I don't want to just talk over a slide where you can just read it, but I will mention some things. The standard form, what's the purpose of the standard form? Well, you could tell me on this one what the degree is without even doing any math work. You just look at it and it tells you what's the degree of this equation right here. 3. How did you know it's 3? It's the highest power. Standard form, it shows you the degree. You could tell me the y-intercept. Do you remember which one the y-intercept is? It's the constant, which in this case is D. Let me go ahead and put that here. That would equal 3. What's the y-intercept? D. Very good. Okay, the cons. The x-intercepts or zeros are not shown. You don't know where they are here. If I come over here, I know where the x-intercepts are. So this is, again, the same equation, but now written in factored form. Do we know where the zeros are? Yeah, it would be the opposites of x minus p, x minus q, and x minus k, which would be positive p, positive q, and positive k. That's what's given to us. But do we know what the leading term is? No, you'd have to multiply out anything that has an x and the coefficient. So a times x times x times x. It would be ax squared. So you would have to do that. And the y-intercept, you'd have to multiply the a times the negative p times the negative q times the negative k. That's the cons to it. But it's two forms. Why do we have two forms? The whole point, why do we have two forms? Different purposes. Different forms for different purposes. Okay, today, what I hope is for many of you, what you go over today is not new. If it seems new, well, then I'm glad we're doing it. That means you didn't learn it the first time. But what we're going to do today is we're going to try to tie in all the stuff we've been working on and just have it really sink in well. Example 1a here, it says find the function, for the function here, find the factored form, degree, in behavior, y-intercept, zeros, and then find where the graph is greater than or equal to 0. We're going to find a whole bunch of things. Let's start with this form. Tell me, do you think this is factored form or standard form? You're correct if you say this is standard form. That is standard form. Now, I'm going to start abbreviating in a little bit. What's weird is standard is abbreviated STD. Try not to laugh the whole time. I know you're high school students, but I'm going to write STD form a lot today. Okay, but that's just the abbreviation for standard form. This is standard form. First, we need to find the factored form. So I'm going to do that first. And I'm going to use numbers just so you can kind of check back as we go through later on the notes. So for the factored form, what you first always look to see if there's a GCF. Does this function have a GCF? Yes. What's our GCF? I heard 2, I heard an x, and then I heard 2x. All three are common factors. 2x is the greatest common factor. The greatest common factor is 2x. So what I'm going to do is I'm going to take my equation and I'm going to divide out a 2x from the other three terms, which means I'm going to perform the exact opposite of distribution. Distribution, you multiply through a parentheses and remove the parentheses. With GCF, you're going to divide out and create a parentheses. So it's exactly the opposite. So what is 2x cubed divided by 2x? I'm doing right now 2x cubed divided by 2x. What's left over? X squared. That's this term. Minus 16x squared. So I'll put the minus already. 16x squared. Yeah, divided by 2x. Minus 8x. Good. And then plus 32x divided by 2x. Plus 16. I agree with that. Now, am I fully factored? No, that's just a greatest common factor. Now we do a second type of factoring. What type of factoring can I do on this trinomial? Let's do the x method next. So for our x method, you need to find your a, b, c, because the top of the x is going to be a times c, the bottom of the x is going to be b. So here's my a, my b, and my c. What's my a if it just says x squared? 1. So 1 is 1 times 16. 16. And then b is -8. Okay, now I'm going to ignore the negatives. I'm going to just deal with whole numbers for a moment. What are the factor pairs? What are the factors that can multiply into 16? What are the whole number pairs? Is what I meant to say. That can multiply to give you 16. I hear 4 and 4. What else? 8 and 2 and 1 and 16. Which of those can somehow combine to be an 8? 4 and 4. It's got to be a 4 and a 4. Now, what makes it become a -8? Now I'm changing my whole numbers to integers. What makes it become a -8? Both are negative. All right, great. This means this equation becomes, don't forget the GCF. We have a 2x times x minus 4. Those are both x minus 4s. They're exactly the same. Do I need to write it twice? So you put a squared on. That right there is the factored form. So compare these two equations. Are these two equations equal to one another, or are they different from one another? They're equal. The math is equal. Now, different question. Are the forms exactly the same, or are the forms different? Different. So why do we have different forms? Different purposes. We're about to see why. So let's talk about the degree. Let's say we wanted to find the degree next. Number 2, degree. If I was going to do degree, which form do you think you would look at to find it the easiest? I would look at the standard form. If you look at the standard form, I'm just going to put this in parentheses, STD form. Again, try not to laugh all day. If you look at the standard form, what's our degree of the equation? 3. You don't even have to do any work. You just say, oh, the answer is 3. Okay, what about in behavior? Now, in behavior, does anybody remember what that is? It's been a few days. It's where the graph is going. Very good. And mathematically, if we're talking about where the graph is going, what symbol or what mathematical notation do we use to talk about where the graph is going? A limit. It's going to be, we're going to use a limit. For in behavior, I'd recommend using the standard form. If you use the standard form, you can predict it really quickly off the leading term. So I'm going to use the standard form here. What is my leading term? My leading term is 2x cubed. So what does that mean? If you think about a graph, 2x cubed, will that look like? Here are the options. I usually just say a parabola or a S-curve. Truthfully, it could look like a line as well. Is it going to look like a line, a parabola, or an S-curve? S-curve, because it's an odd power greater than 1, it's an S-curve. Now, is it an increasing S-curve or decreasing S-curve if the front number is a 2? Increasing S-curve. So that's what the graph should look like. Generally speaking, that's what the graph would look like. Now, if that's the case, we can now discuss about the end behavior. This is where the graph is going. We want to know what's going to happen to my y values as x goes to negative infinity, as x decreases without bound, as x goes left. Any of those words would describe the same thing. What's happening to my y's as I move to the left as x decreases without bound? Well, tell me. This is the one time in math you move on a graph left. What happens as I move left? Does my graph rise, fall, get flat, or come to a point? It falls. It falls to negative infinity. And on the other side, what happens as we go to the right? What happens as x increases without bound, meaning it goes to a positive infinity? What happens to my graph? Rise, fall, get flat, or come to a point? It rises. So those would be my two answers here. So far, I've used standard form twice. Now let's talk about the y-intercept. If you want to find the y-intercept, what's the math we're always going to do to find the y-intercept? Who remembers? You plug in 0. That's what we're going to do. We're going to plug in 0. And I would do it in standard form. Let me do it this way first, just to keep the notes the same. I'm going to plug this into standard form. I think it's easier. I'm going to plug in 0. And so the way to represent that is, rather than writing it out in English, I'm just going to show you the symbol. F of 0 is what I'm going to write down. If I plug in a 0 into standard form, what is 2 times 0 cubed? 0. Minus 16 times 0 squared. 0 plus 32 times 0. 0. What's going to happen if you plug in 0? Anything with an x cancels out. And so all you're looking for is the constant. Does this have a constant? No. So it's kind of like plus 0 right there at the end. That's why it's a 0. So my y-intercept will be the origin. That means when x is 0, y is 0. That's the origin. We got one more little key feature to find. The zeros. Now, which form do you think it's easier to find the zeros from? That's right. You want to use factored form for zeros. This is the key. Factored form, the reason we factor is to find zeros. That's 100% when you use that. So looking off the factored form, I have two zeros. I have a 0 here and a 0 here. This x, the 2, I want you to think of it separate. It's almost like it's x. That 2 is just a value multiplying. I'm not concerned with the 2. What x value if it's x all alone? X equals 0 and x minus 4. What would that be? Positive 4. And you would put m2. What does m2 mean? Multiplicity. Because it happened twice, the graph will be there. Okay, finally, we get to the very end and it says, hey, we want to know, find where f of x is greater than or equal to 0. So the last thing I'm going to do here is I'm going to show you now a more full sketch. Now that I have all these details, we can add in a more full sketch. So I want you to add a x and y axis. And I'll put this as 6. I want to know where f of x is greater than or equal to 0. What I'm going to do is I'm going to put on my zeros. I know I have a 0 at 0. And I know I have a 0 at 4. Put 4 on this side. This is my x axis. This is my y axis, which y is the same thing as f of x. Now, I got that off the zeros. I put on the zeros. Now I'm going to use the end behavior. We know the graph is supposed to look like a S-curve. So how does that S-curve hit all these points? Well, if you use your multiplicity, we can state with confidence that the graph will go up and cross right through at 0. Now, I'm going to pause. Why does it cross through at 0? Because there's no multiplicity, so it crosses right through. Now, as the graph bends and comes to 4, does it cross through at 4? No, with a multiplicity of 2, what should it do? It bounces up, and that's when it takes off to go to increase without bound that we had from there. That's what our graph should look like. Does that make sense to you? That 4 right there. Okay, so last thing. We want to know, where is the graph greater than or equal to 0? The graph is greater than or equal to 0. Oh, sorry. F of x. Is f of x x or y? Y. So if we're looking for where y is greater than or equal to 0, f of x is greater than or equal to 0, y is greater than or equal to 0, do I look up, down, to the left, or to the right? You're looking up. This value over here, this interval, and that interval will be my answers. Now, this has an equal sign. Does that mean I can also be 0? Yes, so I'm going to do closed dots here on my interval. That means I include those. I don't actually have to break the two apart because that's included. It's almost like one consistent group. So f of x, I'm going to use full English here, is greater than 0, greater than or equal to 0 on the interval. Where do I start from? 0, and I'm going to do a bracket because I'm including that value. From 0, I don't have to break it at 4 because that's one consistent piece. I'm equal to 0, I'm greater than 0, I don't have to break it. From 0 all the way until infinity. That's going to be my answer right there. So that's my last answer right there. Okay, so all of that, believe it or not, we've actually been doing this. I'm just trying to put it all together. So everything on there we've been doing. So going through it, these two forms, are the two forms mathematically the same or are they different mathematically? They're the same. So why do we have two forms if they're exactly the same? Different purposes. Some forms are better for one thing, another form, the factored form is better for zeros. Basically, everything else is easier from your standard form. I would say graphing is probably easier from factored form. Graphing and zeros are the easiest things from factored form. Everything else is better from standard form. Okay, that's a whole lot. So let's do it again, but this time I'm going to just give you a simpler problem just so we can go through it quicker. We can just practice the topics, but this will be a lot easier mathematically. So let's just see it again. Example B. Tell me this time, for the function g of x here, which type of form would you call this? Standard form or factored form? This is factored form. How did you know it's factored form? What does factored mean? Factor means to multiply. So that's factored form. It says first find the standard form. Let's find the standard form first. So if I want to find the standard form, all right. First, to get our standard form, all we need to do is multiply that through. So what is 2 times x? And 2 times -4? -8. There it is. The opposite of a GCF is distribution. That's what we did there. So to get standard form, I just multiplied that out. Okay, secondly, we want to know the degree. Now again, to find the degree, which form is easier? The standard form, I agree. I would use standard form. What is our degree on this one? 1. There we go. Let me box up my answers so we can see them as we go clearly. Okay. Answer is 1. Okay, now we need to find the end behavior. For end behavior, again, all of this is typically easier from the standard form other than the exception being zeros or graphing. Those are the only thing that's easier for factored form. So in behavior, I would look at the standard form. What is my leading term? And I'm just going to say LT. I hear 2. It's more than 2. 2x. So if you were to do a quick sketch, what would 2x look like? A line, a parabola, or an S-curve? Line, U, or S-curve? A line. Is it a positive line or negative line? Positive line. So it's going to look like this. So from there, we can get our end behavior. These are going to be limits. Remember, this one's called G, not if. Sorry, G of x. We're going to talk about as x decreases without bound, meaning going to negative infinity. And we'll talk about as x increases without bound, meaning going to positive infinity. What happens as we move left, as we go to negative infinity? It decreases, it falls. So remember the options are it either rises, falls, gets flat, or comes to a point. This graph, as we go left, it falls. What's the symbol for falling? Negative infinity. And what happens as we go to the right? It rises. All right, there's those two answers. There's our end behavior. Now we want to know the y-intercept. Okay, which form do we usually use for the y-intercept? Standard form. And again, this is to find a y-intercept, you just plug in 0. So it's going to be g of 0 equals, if I plug in a 0, everything cancels but the constant, which is -8. Now we arrived here at the end, zeros now. What's the easiest way to find our zeros? The factored form. We're going to look at the factored form on this. So factored form. We have that x equals what value? When you look at the, I can't see the factored form. There it is. What does x actually equal? 4. Okay, from here, now it says find where g of x is greater than or equal to 0. We're going to do this last. So now we're going to come back and g of x being greater than 0. What that means is I'm looking for where the graph is above, below, to the left, or to the right of an axis. If it's g of x greater than 0, what am I going to be looking for? I'm looking for where g of x is greater than 0. Am I going to be looking above, below, to the left, or to the right? Above. So I'm going to be looking where g of x is above. Okay, so I have a 0. Where's my 0? 4. I didn't box that up. Let's go ahead and do that at x equals 4. So 1, 2, 3, 4. There's my 0. I also have, I'm going to add the y-intercept just to get another point. It's at -8. I'm just going to place it down there. I'm going to say that's -8. So my graph should go through those 2 points. And we already said it's a straight line earlier. So my graph should be a straight line going through those 2 points like so. Now, how many intervals is the graph above the x-axis? Is it above right here? 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 Yeah, this area right in here. That's my only portion where I'll have an answer. This time, can I be equal to 0? No, for the interval, I'm going to treat this as an open circle this time. So g of x is greater than 0 on the interval. This time, because I cannot be equal to 0, I'm going to do parentheses 4 to infinity. Last time I used a bracket. This time, let me just show you. Last time I used a bracket because I could be equal to 0. And I did not break it there because I could be equal to 0. This time, since I cannot equal 0, you only approach 4. You don't actually get there. That's my answer right there with the parenthesis. Okay. Yep. All right. Questions over that? All right, as we move into example 2, what I want to show you is how we can tie in some stuff with the calculator. I don't want you to forget your calculator, but we're going to incorporate the calculator into algebra. So first thing I want you to do is open up your calculator. Let's graph this equation. So I'm going to go to new document. I'm not going to save. I'm going to add a graph. Now let's type in this equation. Negative x to the 4th plus 2x cubed. Oh my goodness. Plus 2x cubed minus 13x squared plus 32x plus 48. Now, once you get all that typed in, you can press enter and you should see your graph. One of the things I want you to start watching for when I give you an equation is see if there's a restriction. Remember, a restriction is where it's going to say something along the lines where -2 is less than or equal to x, which is less than or equal to +5, or something like that. Does this graph have any restriction on it? So I don't need to go to the pipe. I don't need to go to control equals pipe. I don't need to do that. I'm just going to graph this in. Because it does not have a restriction, we're not going to zoom fit. So I'm going to change the equation or the y-axis to make it fit without using zoom fit, because zoom fit will not work well for us in this problem. So, because there's no restriction, that's why. Here's my question for you. Let's be smart. If I'm going to change my y-axis, I'm going to go to the y-axis and double click that number. I'm going to the y-axis and I'm double clicking that number. Let's be smart about what value should we put on by looking at this equation. What do you think is a good number to start off at? 48. Why 48? That's the y-intercept. So I'll just pick a bigger number. I'll do 50. Now, is 50 high enough to see the maximum on the graph? No. So we need to go a little higher. How much higher do y'all want to go? You want to try 75? Is that high enough? Yes, it is. If you want to see if anything else happens down here, you can also change this one. I don't know. If you want to do -75, keep it the same. This graph doesn't seem to do anything special down low, so that's going to be my equation. Now, let's go over and see what the instructions tell us to do. Problem says, use your graphing calculator to find the real zeros. Okay, let's find the zeros. I want to make sure everyone remembers how to use the calculator. Press the menu button. Choose Analyze Graph. And then choose 0. When you do Analyze Graph and choose 0, a dashed line should appear that you can move around. It says lower bound. What does lower bound mean? Go to the left. Go to the left of the 0, click the center button. Now it should say upper bound. Go to the right of the 0, click. Are you getting the 0 and -1? Perfect. Let's repeat the process. Go back to menu, choose Analyze Graph, choose 0. Go to the left of the 0, click. Go to the right, click. What 0 do you get that time? 3. Perfect. Those are going to be our 2 zeros. This has 2 real zeros. This graph has 2 real zeros. So the reason I'm using the word real, I'm about to talk about in a moment. Let's write these down here. We have 2 real zeros. 2 real zeros. The zeros occur at x equals -1 and +3. Now, why do I keep hitting this word real? Because look at the equation. How many total zeros should this graph have? Look at the degree, I mean. We should have 4 total zeros. If it's 4 total zeros, that will equal real plus imaginary. So if I have 2 real, how many imaginary must I have? We're going to have 2 imaginary zeros. Now, the problem with imaginary zeros is you can't get the calculator. At least I don't know how to make the calculator give them the values. I would not be surprised if there's a way. I just don't know how to do it. So I know there's 2 real zeros. So what we're going to do on the next slide is we're going to find these imaginary zeros. So is everybody clear on why there's 2 imaginary zeros? Why are there 2? Because the degree is 4. There has to be 4 total. These have 0, they do not have multiplicity. The multiplicity would be considered 1. So that's only 2 zeros. I've got 2 left over. So in part B, we're going to find the remaining zeros, specifically zeros. I'm going to do factors on the other page, on the next page. So I'm going to say right now, I'm going to find the remaining zeros. So here's how I do that. If you know some zeros, what you can do is synthetic division. It's the easiest way to simplify an equation quick. So let's take one of those zeros. Let's just take -1. I'm going to divide -1 into this equation. So let's start writing out our coefficients. Do you all remember how synthetic works? We have -1x to the 4th plus 2x cubed minus 13x squared plus 32x plus 48. After you write those out, leave yourself a space and then draw a horizontal line underneath. All right, so do y'all remember, how do we get started after you write out all the coefficients like this? You drop down the -1 and we follow our mama, meaning we're going to multiply, then add, then multiply, then add. What's -1 times -1? +1. So and now we add and we get a 3. Now we multiply. -3. Now we add. Good. Now we multiply. +16. Now we add. +48. And now we multiply. -48. Now we add. Now 0 is our remainder. Now here's the deal. That is a good thing. Today I'm going to use R of X in the future. For a remainder, I'm just going to call that R of X. This is a good thing. If you get a remainder of 0, do you remember what that means about this? This is a 0, which we already knew that. 0 since, and this time I'm going to just use R of X, since R of X equals 0. And not only that, if this is a 0, then you know what we can state. I'm going to write it over here because I have more room. That X plus 1 would be is a factor. I'm going to write that right there. Since R of X equals 0. That's why. Because my remainder was 0. Because my remainder is 0, that is a 0 and a factor. X equals -1 is a 0. X plus 1 is a factor. Does that make sense to everybody? Now that shouldn't have been a surprise to us because the calculator already told us that. But what it did do is it simplified my equation. I began with an x to the power of 4. Now what do I have? X to the power of 3. Okay, we're going to continue on and now divide out our other 0. Our other 0 we had was at +3. Is that where it was? Now let's divide out our +3. Continue on with the same equation. You just use everything except for the remainder. We're not going to include the remainder this time. So again, we're going to follow our mama. So again, we're going to follow our mama. We're going to do this again. -1's dropping. What's -1 times 3? -3. So I have a +3 and a -3. 0 times 3 is, that gives me a -16. And -16 times 3 is -48. What do we get for our remainder? So if we get 0 for a remainder, what does that mean? What's the factor? X minus 3 is a factor. X minus 3 has to be a factor, and this x equals 3 has to be a 0. That makes sense to you? Okay, all that was a setup to find my 2 imaginary zeros. We had to go through that process to find my, as far as I know, we had to go through this process to find our imaginary zeros. At this stage, what I have is I have a quadratic function that's going to produce my 2 imaginary zeros. Remember how we said there was going to be 4? We've taken out 2. Here's my 2 left over. This is going to be irrational. Or imaginary. I'm sorry, imaginary. We know that because it's not going to hit the graph. You could try to do X method, but here's the problem. Don't even worry about writing this. If you tried X method, here's my A, here's my B, here's my C. What you'd be looking for are factors of 16 that add up to 0. At first glance, you're like, oh, that's great. I know 2 numbers. What 2 numbers? 4 and 4. But here's the problem. They got to add up to 0. How do you make it 0? -4. Now what's the problem? When you multiply, do you still get +16? No, you get negative. So this is going to be imaginary because it doesn't work. So we have to use the quadratic formula. Do you remember the quadratic formula? Do y'all remember this from, oh man, what class was it? I think it was 1-6. Here's the quadratic formula. X equals -b plus or minus square root of b squared minus 4ac, all divided by 2a. That's how we're going to find any imaginary factors or zeros, that, or irrational for that matter, is using this formula right there. Yep. Okay. You take a picture if you can, so I can go as quick as possible here. Okay. All right, so now let's plug in our numbers so we can start to find out where our imaginaries are and finish off this problem. Okay, negative b. What's my b value? I have them right up here. 0 plus or minus square root b squared. What's b? 0 minus 4 times a. What's my a? Hey, y'all should be looking right here. That's where a, b, and c are. Negative 1. What's my c? Negative 16. All divided by 2 times negative 1. Good. We go to simplify this. Negative 0 is nothing. It cancels out. 0 squared is going to cancel out. So basically what I have is a plus or minus square root. What's a negative 4 times a negative 1? There's 3 negatives. 3 negatives are going to become just the same as 1 negative. So I'll make those two positive. It's going to be 1 negative value. What's 4 times 1? 4 times a 16? 64. So this is negative 64. Divided by 2 times 1 is negative 2. Now, look over at my wall where it says domain rules. We've been talking a lot about you cannot divide by 0, rule number 1. What does rule number 2 say? It's about roots. What can you not do with even roots? Can't have a negative number. Do I have a negative number inside this root? This is where imaginaries come from. You can't do this. So what I'm going to do is I'm going to circle the negative. You can't take a square root of a negative number, and so we call that an I. That's the imaginary. I refers to the square root of negative 1. So I'm still going to keep the square root of 64. What is the square root of 64? 8. This becomes 8i. Plus or minus 8i divided by negative 2. So last little simplification, and we're finally done with this slide. If I took my plus or minus, I had someone ask me earlier, what does a plus or minus even mean? That means you have a positive answer and a negative answer. It doesn't mean anything else. It's not like you do some weird math. It's you have both a positive answer and a negative answer. If you take your positive answer of 8i and divide it by negative 2, what do we get? Not 4i. Try again. Positive 8i divided by negative 2? That's negative 4i. But then you take your negative 8i and divide that by negative 2. What's a negative 8i divided by a negative 2? Positive 4i. So this negative down the denominator doesn't actually matter because it's plus or minus anyways. You're still always going to have a positive and a negative. That's my other 0. So we've now found our zeros. All of our zeros, we found them. We had negative 1. We had 3. Now we know I have a positive 4i and a negative 4i. How many total zeros are there? 4 right there. How many of them are real? 2 real. How many are imaginary? 2. That's both a positive and a negative version of the same answer. Now, from that value, what type of form, go to the next slide. What type of form could we write of an equation? If you're given zeros, we could write which form real easy? Factored form. Let's finish this off writing our answer in factored form. Your factored form would look like this. When you write factored form from scratch, there always could be some a value that goes there. Now, we're going to replace a in a second because I know what it is. You don't have to put that, but leave yourself a space. There always could be a value. Normally, you're just going to leave it as an a. And then we plug in the factors. To have a 0 at negative 1, what's the factor actually going to be? Plus 1. To have a 0 at 3, I'm going to have a factor of x minus 3. To have a 0 at positive 4i, I'm going to have a factor of x minus 4i. And to have a 0 at negative 4i, I'm going to have a factor at plus 4i. Now, that would be what you normally write. But this one, I know what a is because this is the a value right there. You see how a is negative 1? All you have to do on this problem is put the negative back in because since we started with standard form, we know what the a is. Now, normally you won't know what a is. If you're looking at a graph, I should say. If you're looking at a graph, you won't know what a is. But if they give you the equation, this is the a. And that's why I'm going to put a negative right back in the front. There it is. That's called a linear combination. Why they call it linear combination is each factor is linear all the way through. All right, quick review. What do you use factored form for? Zeros. And if you wanted to graph, the factored form is easier for that. What do you use standard form for? Just about everything else. Degree, y-intercept, in behavior, all those things. Okay? Now, we've been doing just polynomial functions here. Now, let's tie this in. Oh, I'm getting ahead of myself. I want you to determine if x plus 2 is a factor of this. DOL number 1. Question's going to be, how do you know it's a factor? I want you to show me whether or not it's a factor. It's a quick mathematical process. You could use graphing. I don't want you to use graphing. I want you to determine if this is a factor. Think through another way of determining if it's a factor using algebra. I'll walk through them. DOL number 1. Looking at rationals. So here's what I want you to recall with rationals. A rational, all it is, it's a polynomial divided by another polynomial. So today I slowed everything down and I went and I looked at polynomials. What we're going to do with rationals, it's the exact same math. It's just you do the polynomial in the numerator and then you do the polynomial in the denominator. So once again, these two equations, guess what? They're equal to one another. These two are equal. Goodness gracious, it won't write. These two are equal to one another. Each, the standard form and the factored form, have their own pros and cons. But the equations themselves are equal. They're not different, they're equal. They have different forms because we have different, y'all didn't repeat it. Different forms for different purposes. Okay. So now, example 3. Let's talk about this form right here. What is this in, factored or standard? This is standard form. This right here is standard form. So part I here, it says find the factored form. So to find the factored form, it's going to be the same equation. The same exact equation. It's just going to look different. Let's talk about the numerator. This numerator can be factored because it's quadratic. I can factor it. This is like A. What is -4? B or C? C. It's a constant. It's C. So what is B? Okay, so in my my x, I will put a -4 at the top of my x and a 0 at the bottom of my x. What are my whole numbers that can multiply, my whole number pairs that can multiply and give me the number 4? 2 and 2 or 1 and 4. Which of those two can combine to give you a 0? How do I make 2 and 2 combine to be a 0? One's negative, one's positive. Okay, so are those exactly the same? No. So I need to write them both out individually. I need an x plus 2 and I need an x minus 2. Now let's take a look at the denominator. What goes at the top of my x this time? 10. What goes at the bottom? 7. Okay, once again, what are my whole number pairs that can multiply to give you a 10? 10 and 1, 5 and 2. Which values are we going to use this time to give me a 7? Okay, I'm going to put 2 first, not that it matters, but it'll just make my equation look cleaner in a second. And what about positives and negatives? Both positive. So I go to put these in parentheses. I'm going to have an x plus 2 and a x plus 5. Now, pause. That right there, without doing any math, that's the factored form. A true factored form needs to be mathematically equal. So I have a question for you. Hear me. To be a true factored form, they have to mathematically be equal. If I did this, are they still equal? No, the math has been changed. So a true factored form would be like this without simplifying at all. Do you follow that line of thinking? Okay. Now we're going to find all those values, but I think it's much easier to look at the factored form to find them. Remember, this is just a polynomial divided by a polynomial. So in the numerator, usually the factors find what we call zeros. The denominator, it's not going to be zeros because rule number 1 on the wall. What are you not allowed to do with division? Divide by 0. So what was a 0 in the denominator is not going to be called a 0 anymore. We're going to call it something else. All right, let's first begin with this. What could I do to this equation? I'm just going to copy it over. I'm going to copy it and paste it so you can see that is the true factored form right there. That's the factored form. But now what I'm going to do is I'm going to mess with my equation a little bit. What do you see happens when you look at this equation? We have a hole. What's the hole? The 2 that cancel out. We're going to have a hole when x equals -2. Okay, I'm going to hit all the details before I start writing them out. What else do you see this problem will have? A vertical asymptote. When x equals what value? Now these are the 2 spots the graph's going to break. The graph will not exist. It's undefined at the hole and it's undefined at the vertical asymptote. These are going to break the domain, those 2 values, because they're from the denominator. That's where the denominator is dividing by 0. What do you call this one up here? That's the 0. So our 0 is going to be x equals 2. So now I'm going to start writing out my values. Okay, domain. You just heard me say it. With rational functions, it's a polynomial divided by a polynomial, which means it should seem like it's going to be all reals divided by all reals. The problem is there is one value you're not allowed to divide by. What are we not allowed to divide by? 0. In this equation, what values of x would give us 0 in the denominator? -2 and -5. Those are the only 2 values x cannot be. We will have a break in the graph at -2 and -5. I'm going to go in numerical order. So I'm going to do the most negative first and then the least negative second. Those are the 2 values x cannot be. What can x be? Everything else. That's an XER. X is an element of the reals. So x cannot be -5. It cannot be -2, but it can be every other single value. That's our domain. Did this problem have any holes? Yeah, we had a hole at what value of x? Now a hole is going to be like a point. So, oh, there it is. So we need to find the x value. The y value, I'm sorry, the y value. Do you remember how to find the y value? You plug in, oh, I hear plug in the 0. Plug in, be more specific. It's not a 0. You plug in the hole to the reduced equation. So the y value would equal, you plug in the -2 into this equation right there. So I don't need the parentheses anymore. Parentheses mean multiply. I've canceled out what it was multiplying with. It'll be a -2 minus 2 more over -2 plus 5. What's -2 minus 2 more? -4 and -2 plus 5? 3. It'll be -4 over 3. Did this graph have any asymptotes? We do have asymptotes. First off, we have vertical asymptotes. We have vertical asymptotes when x equals -5. Now this graph also, rationals usually have a horizontal asymptote most of the time. Only if the degree is bigger on the top do we not have a horizontal asymptote. So this one does have a horizontal asymptote because if you look at the standard form, if we look back at the standard form, are my exponents the same? Am I bigger on the bottom or am I bigger on the top? Exponents are bigger, are the same. I'm sorry, I can't talk. They're the same. This will also have a horizontal asymptote. Now a horizontal asymptote, or rather, I should say, all in behaviors. When you compare your exponents, all of them will be y equals. Always, 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 it's y equals something. This horizontal asymptote, because my rule was the exponents are the same, if your exponents are the same, you divide your coefficient. So it's going to be y equals, what's my coefficient from the numerator? this coefficient, what's my coefficient in the numerator? 1. What's my coefficient in the denominator? It's just 1 divided by 1, which is what value? 1. We'll have a horizontal asymptote at 1. Finally, intercepts. So the different types of intercepts, you could call it an x-intercept. We typically call it a 0. Where was our 0? Can't see it now. I'm scrolled down. X equals +2. Do you remember how to find the y-intercept? You plug in 0. To find the y-intercept, you plug in 0. So this equation was called f. So we'll write f of 0. And when you plug in 0, use your standard form. Everything cancels out. That's not a constant. So it'd be -4 over 10. -4 over 10 is all the constants. So it'd be -4 divided by 10. Does that reduce? It does. What goes into both of them? -2 over 5. So there's all of our answers. I didn't box up a single one of those. Whoops. There we go. All right, that was the exact same math. I know it seems like it takes forever to do one problem, and that is a true statement. It does take forever to do one problem. But it's the exact same math we were doing with polynomials, because a rational is a polynomial divided by a polynomial. So it's the exact same math. Exact same math. All right, I have just one more like this. I promise after this, we'll be totally doing different things. Let's knock out one more, and then we'll get to take a look at some different things here. Go ahead. All right, let's look at part B here. What form did I give this to you in? This is standard form. This is standard form. It says find the factored form. So we're going to first try to find the factored form here. Oh, they didn't call this f, sorry. They called this one k of x. We're going to try to find the factored form. Let's start with the numerator. How could I factor that? X method? What number goes at the top of my x? -12. What goes at the bottom of my x? Okay, what are my whole number pairs that can multiply and give me a value of 12? 3 and 4 is 1. 6 and 2. 12 and 1. Those are the only three those are the three sets of options. 1 and 12, 2 and 6, 3 and 4. Which one will give us a -1? 3 and 4. And to make it a -1, it's a -4. Okay, so this would factor as x plus 3 times x minus 4. Now the denominator, technically you cannot do x method yet, because x method you have to have a even leading term. That's odd. So I have to be able to do something else first. What can I do first? GCF. If I did a GCF, what is common all the way across? X. So I divide out x from all these terms. So I'm left with x squared plus x minus 20. Now can I don't want to forget this x. I'll put the x there. Now can I do x method? You bet. What goes at the top of my x? -20, bottom 1. So factors of 20 that add up to 1. What are my whole number pairs? 5 and 4, 10 and 2, 21. Those are them. Which one's can combine to be a 1? Okay, 5 and 4. And I see the 4 is second. Someone puts 4 second. Not that the order really matters here. What makes it a 1? A -4. So I'm going to have an x plus 5. And I'm going to have a x minus 4. Now, truthfully, should I, if it says find the factored form, should I cancel it out? No, I should not cancel it out. Why not cancel it out? Oops. Because would it be mathematically equal if I canceled it out? No. But what we will do is when we go to find these key details, then we will cancel it out. But as far as the answer goes, the factored form itself, you would leave it as it is. The factored form itself, you would leave that as it is. Now, find all this stuff. Let's start simplifying. What can I cancel out of there? What does that become if it cancels? We have a whole when x equals 4. That's right. Okay, what about the values that do not cancel? Those are vertical asymptotes. So we have 2. When x is by itself, that would be a 0 and a -5. Good. Okay, what do you call something that doesn't cancel out in the numerator? That's a 0. When x equals -3. All right, if I try to roll through this, domain comes first. What are the only values of x that will not exist? Because remember, with a polynomial is supposed to be all reals. This is a polynomial divided by a polynomial. You would think, since it's all reals divided by all reals, it would be all reals, but it's not. What's the one value you cannot divide by? You cannot divide by zeros. So where do I have zeros? 0, -5, and 4. I'm going to go numerical order. I'm going to say x cannot be -5, 0, or +4. What value of x can the graph go through? Anything else. X is all reals other than those values. Did we have a hole? We had a hole when x equals 4. So we got to find the y value. How do you find the y value? You plug in the 4 to the remaining equation. So it'll be, again, I don't need the parentheses in the numerator because parentheses means multiply. We've canceled what it's multiplying with. So it's just 4 plus 3 over. I do need the parentheses in the denominator. 4 times 4 plus 5. 4 plus 3, that's 7. Help me out down here, though. 4 plus 5 is 9. What's 4 times 9? 36. So it's going to be 7 divided by 36. Asymptotes. We have 2 vertical asymptotes there. At x equals, I'm going to go in numerical order this time, -5 and 0. I need to be boxing these up as I go to make it clear what my answers actually are. Those are my vertical asymptotes. Now this one, for horizontal asymptotes, for the end behavior, I again will have a horizontal asymptote, but it's going to be a different rule this time. I want you to go back up and look at this standard form. Tell me about my exponents. Are my exponents the same? Am I bigger on the bottom or am I bigger on the top? You're bigger on the bottom. So bigger on the bottom follows the rule Bobo. Bobo means if you're bigger on the bottom, it's y equals 0. That's your asymptote, your horizontal asymptote. It's y equals 0. Finally, we made it to the end. An intercept. Do we have any x-intercepts? Slash, same thing as a 0? Yeah, when x equals -3, that's right. At x equals -3, we have one. What about a y-intercept? How would you find the y-intercept? You plug in 0. This one's called k, so I'm going to do k of 0 would equal. When you plug in 0, remember, use their standard form. Everything that has an x simplifies out. So what's the constant left over here? -12. What's the constant left over in the denominator? There is no constant, so it's kind of like a 0. So it's -12 divided by 0. -12 divided by 0. Well, what is anything divided by 0? Not 0. Undefined. So guess what? There is no y-intercept. This graph would not cross the y-axis. You could also box up k of 0 is undefined. You could box that up as well, but there will be no y-intercept. All right. We went through a ton there. Hey, roll it back through. When do I use factored form? Find zeros. If I had a graph by hand, I would also do it there. When do you use standard form? Everything else. Okay, great. On a rational, where do you find zeros? Numerator, where do you find vertical asymptotes? Denominator, where do you find holes? Both, top and bottom. All right, good. All right, this one here. Sorry, I'm looking for something. I guess it's coming up later. All right. Example 4. I've given you a graph. And it says write an equation, and I give away how to do it. If you are looking at a graph, what's the easiest way to write an equation from a graph? Which form? Standard or factored? Factored form. You can write an equation from factored form. Let's call out, technically there's 5 key features here. You only need 4 of them to write the equation. I'm going to walk you through which 4. Call out any key feature you see when you look at this graph. A 0. Where do you see a 0? Okay, put that on there. This x equals 3 is a 0. Now, tell me, what factor would that come from? X minus 3. Now, for the equation, we're writing an equation. F of x equals, leave a space. Now, technically, there could be some number. A lot of times we'll do like an a over b. But truthfully, since we don't know what either one are, I'm just going to put an a out front. There could be some number that multiplies here that I don't know, and I don't care what it is right now. I just don't care. Where would I put the x minus 3? And the numerator. Yeah, I'm going to make this clear. Whoops. Didn't mean to do that. I'm going to change this for the sake of the notes. I'm going to change this to color real quick, so you can see where it goes where better. I'm going to make that black. Okay. So x minus 2, you said, or x minus 3 needs to be in the numerator. I totally agree. Let's put that there. Okay, what other key feature do you see in this problem? A hole. Where's the hole located? Four comma negative 1/2. That is a hole. What factor would that hole come from? X minus 4. Where do I place x minus 4 if it's a hole? Top and bottom? Okay, we need both of that. What other key features do you see? And here, a vertical asymptote. The vertical asymptote is located when x equals what value? 2. What's the factor that generates that? Oops, x minus 2. And where would that be located? Denominator. This would be x minus 2. Now there's one more key feature on this graph. The horizontal asymptote. It's at y equals -1. Now this does not come from a factor. This comes from a rule. If your horizontal asymptote is -1, let me write down the rules. You could have exponents are the same, where you divide your coefficients. You could have bigger on bottom, which would be y equals 0, or bigger on top, where it's not horizontal at all. It's oblique or slanted. What's the case this time? Is it that we divided the coefficient? Is it that the value is 0? Or is it that it's not horizontal at all? Which of those 3 cases is it? Okay. Is this horizontal? Okay, it's horizontal. So that means that's not that one. That means not horizontal. It's not that one. Is this number 0? No. So what does it have to be? This has to be eats DC. So here's what that means. You remember how I said there has to be some number that the coefficients, when you divide them, you get -1? Guess what I can do here now? I told you didn't have to know it, but I could put a -1 there if I wanted to, or do you actually have to even put -1? You could just put a negative. You can put it with the top, the bottom, or in the middle. It doesn't matter. Mathematically, a lot of times with fractions, we put it in the middle like that. It's a -1. That's what. So let me write it this way. If it's a divided by b equals -1, and that's where that symbol came from right there. Now, don't stress over that part, but that's how you get that. Okay, let's try it again. I got a second example. What key features do you see? Zeros, how many zeros do you see? 1, 0, where's it located? At x equals 1. Okay, so if that's a 0 at x equals 1, what factor did that come from? Okay, we're going to write the equation g of x this time. Now, again, leave room. There could be some a, or technically it could be a divided by b. Since we don't know what either one of them are, I'm just going to put a out front. Where would x minus 1 be located? Numerator or denominator? Numerator, x minus 1, great. Okay, call out. What other key features do you see? A hole. This hole is located at 2, 1/2. What factor would that hole come from? X minus 2. Now, where would the x minus 2 factor be located in my equation? Top and bottom. X minus 2 and x minus 2. What else do you see? A vertical asymptote. Let me do that again. A vertical asymptote. What x value is that? 3, which means it came from the factor x minus 3. This one, believe it or not, has another vertical asymptote. Do you see it? At 0. Very good. This graph also has a vertical asymptote right in here. You can tell the graphs are going to infinities. That means there's another vertical asymptote. If the graph goes to infinities, there has to be a vertical asymptote. We have another one when x is 0. So what factor would that come from? If it's 0? Just an x all by itself. Any other key features we need to hit? Horizontal asymptote. Tell me about the horizontal asymptote. If our horizontal asymptote is y equals 0, what's the case for the degrees? Are my exponents the same? Is it bigger on bottom or is it bigger on top? Bigger on bottom. It's got to be bigger on bottom because it's y equals 0. Check it out. Are my x's bigger on the bottom? This is factor form. You got to add up all the x's. How many x's would I have? 3. How many x's here? 2. Are my bigger on the bottom? Then that's good. I'm content with saying this is your answer right here. However, you could solve for a. How you would solve for a is, remember, the hole, you'd use the hole. That's what you would do. That if you plugged in 2, you could solve for a. What value do you know is we need to get as an answer? 1/2. That's to solve for a. To solve for a. I'm not going to do it, but here's how you would do it. Is you would say 1/2 equals a times, and that you would plug in the 2. 2 minus 1 over 2 times 2 minus 1. You would solve that right there. That's how you'd find out what a is. And a on this one is also -1. Do y'all want me to do the work or no? Just to show it one time? Okay, what is 2 minus 1? 1. When you multiply, that can go up on top. So I'm going to say that's 1/2 equals. That becomes 1a. That becomes 1a. What is 2 times 1? 2 times 1 is 2. Well, I'm getting a different number here. Why am I getting a different number? I somewhere did something wrong. Plug in a 2. Those cancel. 2 minus 1, 2 minus 3. That's where my mistake is. There we go. 2 minus 3. Sorry, I was like, I did something wrong. Okay, let's do this again. What's 2 minus 3? -1. 2 times -1 is -2. Okay, -2 goes down there. Now, how do I solve that? What's the last step to get a by itself? Multiply by -2. And what happens is the 2's over here cancel. And so what does a actually equal? -1. That kind of got messy on the left side. I'm going to take that off. There we go. Those cancel off. And so a equals -1. And so one more time, you could have a negative there. That's just kind of coincidence that that was our last one. But that's how you would do it. Do you actually need to solve for a? Is that going to matter much for you? No, that was extra just to show you how it's done. You just plug in numbers. You plugged in a value. I plugged in the whole because that was just an easier equation to do so. All right. We've gone through a ton. To end the class, we have some oblique asymptotes to talk about. This is the case of Botten. Go ahead and write down Botten next to this. Botten. What does Botten stand for? Bigger on top. If your power is bigger on the top, it's not horizontal. The n itself means not horizontal. It's not a horizontal asymptote. Instead, it's going to be an oblique or slanted asymptote. It's not horizontal, but oblique. Now, what does oblique mean? Oblique means slanted. Okay, so we don't have much time to go through this, but just look at this equation here, or this graph, this asymptote. Is that a horizontal asymptote? No. We could do our algebra 1 to get the equation for this really quickly. What's the slope here? If you what's the slope? How much rise is there for every run? 1. It's 1 over 1 x plus, what's my y-intercept? 1. Here's my equation. It's y equals 1x plus 1. That's my oblique asymptote. Now, mathematically, how could you get this? The way you get this is you divide the denominator into the numerator. If you go to the next slide, I actually showed you all the work. Oh my goodness, look at all this craziness. I took the numerator right here, but notice, do I have any x squareds? I put a 0x squared, and I didn't have a constant, so I put a 0. And I just did long division, and I got my answer. If you look down here, you'll find out that that's the quotient. The quotient is the asymptote. Did we just get x plus 1? That's how you do it. Now, you don't have to do long division. You could do synthetic if you factored it and simplified. I'm going to do synthetic really quick. Watch. You ready? It's going to go fast. If you had it in factored form, what could I do to my factored form equation? No. Here's standard right there. I already have standard. What could I do to my factored form to make it more simple? Cross it out. If you cross that out, now what are we dividing by? X plus 1. And what you could do is you could say, okay, well then x equals -1. And you could do a synthetic. Now I would need to multiply this out. What's x times x? For the sake of time, I'm going to put 1x squared so you know. X times 2 is a 2x. And there is no constant. You need to have a 0. If you drew your line, look, you're going to get the same exact value. Watch what happens. I drop the 1. It becomes 1x. What's 1 times -1? -1. This simplifies and gives us. And guess what? And you multiply there, you get -1. That's a remainder, and that means it's not a factor. It's not a factor. Is it a factor? No, it's not a factor. That's why it's a oblique asymptote. But look what we just got for my equation. You see how I got the exact same thing? 1x plus 1. So you can use synthetic, you can use long division. That's how it works. We don't have much time, so let's try to do this 5a as quickly as possible. All we're going to do is I'm going to find my oblique asymptote here. First off, this won't cancel, so that is a vertical asymptote. I'm going to go ahead and put that because it says any asymptotes. The vertical asymptote there would be x equals what number? -1 How do you get rid of the 2? Negative 1/2. That's my vertical asymptote. Define my end behavior. You use your rules. This time, am I bigger on top, bigger on bottom, or the exponent's the same? Bigger on top. If it's bigger on top, it's not horizontal. What's it going to be instead? An oblique asymptote. I'll go ahead and write that out since we don't see it very often. So define your oblique asymptote. You take your divisor, x equals negative 1/2, and you divide it into this equation here, the numerator, which I have 6x squared plus 1x. I put the x just so you can see what these values are, and then a plus 5. Leave a space, draw a line. How do I begin from here? Drop down to 6. So 6 times negative 1/2 is negative 3. Now I add negative 2. I multiply. Negative 1/2 times negative 2 is a positive 1. What do I get there? 6. That's your remainder. Is this a factor? No, it's an asymptote, not a factor. So 6 is our remainder. This was an x, x squared. What's it now? X. One last thing though that's weird with this problem. Rule of synthetic. If you're dividing by a fraction, at the end you need to divide everything by, not everything, you need to divide the quotient by 2. So my oblique asymptote would actually be y equals 3x minus 1. That would be my asymptote right there. My oblique asymptote. That's a weird looking A, but that's what that was supposed to be. All right, and our last example to look at here. One more time, if we want to find equations for any asymptotes, the thing to do is to try to factor it first. I didn't even factor this last one. I kind of recognized that nothing was going to cancel out. But if you were to factor, here's what you would learn. So I'm going to factor both the numerator and denominator. I can first see that I have a GCF here. So I'm going to have a GCF of x. So if I pull out the x, I have x squared plus 4x minus 12. Okay, and now I can go further and x method this right here. We're looking for factors of negative 12 that add to be 4. So 1 and 12, 2 and 6, 3 and 4. The values have to be a 2 and a 6. And to make it be a positive 4, the 2 needs to be negative. So this is going to be, let me write k of x down here. K of x will equal x, our GCF, times x minus 2 times x plus 6. And now we can factor our denominator. So I have factors of 6 that add up to 7. So out of 1 and 6 and 2 and 3, it's got to be the 6 and 1. So when I factor this, I'm going to have an x plus 6. Actually, I'm going to write the 1 first. X plus 1 and an x plus 6. Okay, so when I look at this equation, first off, we're supposed to find asymptotes. So this right here is nothing for us. It's a hole. Since those cancel out, and we're not really concerned about the hole because we're looking for asymptotes. So right here, we have a vertical asymptote. That's one of the answers we're looking for. We have a vertical asymptote when x equals negative 1. That will be an answer for us right here. And now this one, because my power is bigger on the top, because I'm following the rule Botten, because my rule is Botten, bigger on top, no horizontal asymptote, we're going to have an oblique asymptote. I'm going to have an oblique asymptote. And so again, to find that, what I can now do is do synthetic division. I'm going to take my x equaling negative 1, and I will divide it into my leftover equation. So again, if you multiply this through, I have an x squared minus 2x. So I just distributed that, and there's no constant, so you can do it like plus 0. I'm going to leave a blank. Draw a line, and we're gonna start solving all this. So my 1 drops. 1 times -1 is a -1. This becomes a -3. -3 times -1 is a +3. That is my remainder, and that's what I'm expecting to have a remainder because it's not a factor. It's a asymptote, not a remainder. I mean, not a factor. It's an asymptote. So this was x squared. This is an x now. Since it's not a fraction, I don't have to worry about dividing. That's going to be my equation right there. My oblique asymptote is going to be my oblique asymptote here. I'll go ahead and just rewrite it one more time. My oblique asymptote will be y equals x minus 3. And that's that equation there. So with that, you've seen the whole lesson. I have 2 DOLs to go over. One of them you can think of this problem here. I want you to take a look at the equations and make a statement about specifically start with the asymptotes. Would this have a horizontal asymptote? That means either BOBO or east DC. Or is it slanted, meaning it's a bottom? Take a look at your equation, go from there. Once you decide on that, then go off of the holes and vertical asymptotes. You could factor to find that. And finally, after you do this DOL, second DOL, I want you to think about, remember, a limit doesn't tell you where the graph is, it tells you where you're going. So this tells us about our right end behavior. This tells us about our left end behavior. These with the minus and the plus, remember, that means it's coming to a break. There's going to be a break at -1. Those values will let you know if it's a vertical asymptote or a hole. But as you approach -1, the break at -1 from the left side, this is what your graph's going to do. As you approach the break at -1 from the right side, this is what the graph's going to do. If you graph it, or you could put that together as a graph and have a pretty good idea what the graph should look like. I'll let you do that, and then you can go online and do your DOLs through College Board.